Hi, welcome to Lesson 16 of our Math 135 course. Today we're going to look at the first lesson in graphing rational functions. There's quite a bit to it and it might be kind of new to you, and so I thought it might be a good idea to go ahead and split that into two parts. So to start out with, and on these first couple of graphs, you may want to pause me and go ahead and take a few minutes and see if you can graph it. In my classroom setting, I like to have the students just try to graph it using a table of values and see what they get. Of course, a lot of times what we start out with is, well, what if x is 0? So I put that in and then I look at it and say, well, I got a problem right away. I cannot let x be 0. Well, that creates a problem. That means that my graph will be nowhere along that y-axis because it's totally undefined along there. Well, that seems kind of odd, but let's just try some other values, some nice ones. Well, if I put in a 1, I get out of 12. Put in a 2, I get out of 6. Put in a 4, I get out of 3. Okay, I kind of have an idea of what's going on there. Now, 112 is a little bit high for my graph, but I could put in 2, 6. I can put in 4, 3. And by the way, I know 3, 4 is on there as well. I know 6, 2 is on there. And if you think about the location of those others, 12, 1 is going to be out here a ways, and 112 is up here a ways. So I get kind of an interesting curve going on there. Even though this has an exponent of 1, there is no straight line going on here. Hey, and by the way, you might realize that, okay, this is different than the linear functions that we've worked with before, because notice the location of that x. Since he's sitting down in the denominator of a fraction, that brings up a totally different situation. And it's going to be called a rational function anytime you have a polynomial in the numerator and a polynomial in the denominator. That becomes a rational function. And each of these is a polynomial. So this becomes a rational function. And apparently, they act differently than lines. Okay. Well, I know I can't use 0, but what if I go over to the negative side? -1, I get -12. Okay, that's way down there below my board. -2, -6. I can put that one on. I can put -3, -4. Oh, you know what? It's kind of interesting. I realize that as I change the sign on x, I'm going to get exactly the same value out, only the sign is switched. Now, do you remember what that means as far as symmetries are concerned from a lesson way back there? It means I have symmetry with the origin. Okay, so apparently I've got all of this stuff going on, and I've got two curves. They're going to kind of look like this. There's one part, and here is one part. And somehow I can't touch that y-axis. Well, I wonder if I can touch the x-axis. So how do I get an x-intercept? Let's see, you put in 0 for y, right? Okay, so let's try that. I'd have 0 equals 12 divided by x. And if I multiply that x over, I get 0 equals 12. Well, since that's never true, it means there are no x-intercepts. So this is kind of interesting, a graph that has no x-intercepts and no y-intercepts. Well, it does make sense that this thing continues to fall. And this is one of the reasons why I like for you to play around with maybe many more values than you could put in this table to get a feel for what's happening. Like if I put in 24 for x, I get out of 1/2. What if I put in a 200? What if I put in 1,000? you realize that I'm always going to get a positive number out. As I go out to the far right here, and I keep putting in bigger numbers for x, I will always get a positive number, but they're getting smaller and smaller and smaller. But they can't ever hit 0, can they? Well, that brings up a very unusual situation, one which we call an asymptote. And I put a dashed line across there because that line is not part of the graph. It's a feature that helps me understand the graph, but it's not part of the graph of this function. Now, the word that I just used there is asymptote, asymptote. And you might have heard that word before. Now, what an asymptote helps me understand is end behavior. It helps me understand that as I'm going far out there to the right, this curve is going to snuggle right up next to that red dotted line. He's never going to touch him, though, as you go far out there to the right. Now, what as we're going off here to the far left? What if I put in -1,000,000, -1,billion? You realize that a positive divided by a negative, this answer will always be a negative, but it's going to be very, very tiny in absolute value. It's going to be approaching 0. All right. Well, what's kind of cool about this is by all this reasoning, I can figure out what's happening to this graph. Now, there's still one more place that I need to look because apparently it's acting very strange at the y-axis. So let's think about this. As I'm putting in numbers for x that are smaller and smaller and smaller, what happens? Well, I know when I put in a 1, I get out a 12. What if I put in 0.1? So I'm getting kind of close to 0. 12 divided by 0.1, I think if you double check that, wow, that's 120. Well, what if I go closer to 0? What if I put in a 0.001? Well, I think if I'm doing my arithmetic right, we get 12,000. So apparently, as I put in numbers closer and closer to 0, I'm getting these huge values. And it does make sense because I've got this set quantity that I'm going to divide by a very tiny number. So it's getting huge. And guess what? The reflection happens over here because if that x is a very tiny negative, when I say that, I mean tiny in the sense that if you ignore the negative sign, like a -0.1, something close to the origin there, I'm going to get a negative value out, but it's going to have a huge value. So in fact, I've got a vertical asymptote. And again, asymptotes are about end behavior. Because you see, if I'm looking in close to the origin and I'm looking in where the numbers are nice and small like we usually do, I can get a good handle on that graph. But I also want to understand what happens when it goes way far away from the graphing window that I'm looking into at this point. Okay? Well, that's a pretty cool looking graph. Oh, by the way, he has a cool name. He is called a rotated hyperbola. Perhaps in an Algebra 2 class in the past, you might have studied hyperbolas. And if you take your head and kind of rotate it 45 degrees, you'll see the hyperbola sitting there. And that's why it's called a rotated hyperbola. Okay, that's kind of cool. Well, now what we want to do is go over to 12 divided by x squared. Now you'll notice that it's exactly the same equation, only now I have a square down in the denominator. Well, you know, I still can't put 0 in, and I still can't get 0 out. Ooh. So let's try some other values. What about when x is 1? Well, I get 12. What if x is 2? 2 squared is 4. I get a 3. These may not stay nice for very long. If I put in a 4, I get 12 over 16. What's that, about 3/4? Boy, he's dropping pretty fast, isn't he? Will he ever go negative? Like if I put in 100, what happens there? That'd be 12 divided by 100 squared. Well, whatever it is, it's getting pretty close to 0. Okay, so let's graph this. We have the 112, which is way up there somewhere. We've got a 2, 3. We've got a 4, 3/4. And then it's going to be going closer and closer and closer to 0. Hey, so what do you think's happening here along the x-axis? It's a horizontal asymptote because this curve is going to keep getting closer and closer and closer and closer. Hey, by the way, one of the things you may not realize is just how dense that number line is, okay? We often think, well, there aren't very many numbers between 0 and 1. Oh, yeah, there are. There's infinitely many. In fact, it's very cool. You can think of it in this sense. Between any 2 points on that number line, there's a middle, there's a midpoint. Well, then between those two, there's a middle. Well, between these 2 points, there's a middle. And I can play that game until the end of time. So that means that this curve can keep coming closer and closer and closer and closer and never touch. It's really a pretty deep idea. Well, hey, if you think about what we've studied in the past on symmetries, you might realize that this guy is going to have a symmetry. Now, the reason is, as I change the value, as I change the sign on x, I'm going to get the very same value out because that squaring is going to wipe away any negative. For example, if I put in -1, well, I square that, I get a +1. I still get the +12 out. If I put in -2 and square it, I get a 4. I still get +3 out. Okay, and so in fact, I've got this really nice symmetry with the y-axis. That's very cool. Now again, as you consider what happens as x gets really close to 0, as x gets really close to 0, this thing is going to get huge. And realize it doesn't matter if it's approaching 0 through positive values or through negative values, because I square that, I can take a very tiny negative or a very tiny positive, put it in here, and I'm going to get a huge value out. So I do have 2 asymptotes. I have a horizontal asymptote here, and sometimes we abbreviate that with HA. Horizontal asymptote is y equals 0. You want to give a whole equation on that. I also have this nice vertical asymptote going on. We can abbreviate that, and that would be x equals 0. Very cool. Okay, well, let's continue. As we go to this particular equation, you might notice I keep with that 12. It's just because we're investigating, and I don't want to suddenly have all kinds of crazy things going on. And in fact, let's see if you're up on your transformations. How does this equation compare, how does the graph of this equation compare to the graph of this equation? Essentially, you have to ask yourself, so what does that minus 3 do to the graph? Well, you might notice he's definitely hanging out there with that x. That is your horizontal shift. From way back in our transformations, that's that c value. So if you wanted to, you could go back to our graph for 12 over x and say, oh, all I'm going to do is slide it 3 to the right. And interestingly, what does that do? Well, it slides my vertical asymptote 3 to the right. Hey, if I do a slide 3 units to the right, would that affect that horizontal asymptote at all? Well, I guess in a way he slides him, but it doesn't change his location at all. That horizontal asymptote is still going to be the x-axis. And you can take some values and plot them, but I think you could find out very quickly that the rough idea is he's going to look like this, and he's going to come down into this region. Now, you know what? Since I know he's coming down through here, I'm thinking, why don't I find his y-intercept? Because you know, y-intercepts and x-intercepts are good points to find. So for my y-intercept, let's see, I put 0 in for x. Well, put that 0 in and we get -4. So 0, -4, and this guy is going kind of like this. So I've got the 2 pieces of my rational function. Now we need to talk about some other basic stuff here. For example, you want to consider domain. You know that nasty, nasty word from back talking about functions. What is the domain of this particular function? Well, it's going to be all real numbers except 3. Now that means that your graph must consider what will be happening for x values from -infinity to +infinity, and we know that at +3 there will be no function value. Hey, by the way, that doesn't always mean an asymptote. To clarify that you have an asymptote going, you want to ask some questions like what we have right here. And I know that notation might look totally frightful. In fact, it might look totally insane. But I'll help you with it. The way you read this notation is, as x approaches 3 from the left. You know, you might have thought that I just got totally whacked and I meant to write -3. This is kind of odd. If you see the negative sign coming after the number and up as kind of a superscript, that's going to indicate to you from the left. Well, then what do you bet a plus sign up there would mean? From the right. Remember, I've told you repeatedly, we're just daggum lazy when it comes to writing. So what this is saying, as x approaches 3 from the left, where is the function going? It's saying f of x is approaching what? Okay, so here's what you want to do. Here's where x is 3. Okay, there's my 3 on the x-axis. Any of those points have an x-coordinate of 3. So you want to kind of be riding the curve, like you were a little bug in a little bitty car, riding along that curve. Where are you headed as you're coming in towards 3 from the left of 3? Well, it appears that I'm heading right down towards -infinity. And I like looking at it from the graph, and then let's also think about the equation. What happens if I put in here a number that's just a teensy bit smaller than 3, because all the numbers on the left of 3 would be smaller than 3. Something like, say, 2.9. Well, you realize that you get a really small number, and because you're subtracting the 3, it's going to be negative. So I get 12 divided by a teensy negative number, heading down to negative infinity. Okay? And I write that with a nice little infinity sign, kind of like a tipped over 8. Well, this notation says, okay, as x approaches 3 from the right-hand side. So if you're going to look at the graph, it's a matter of I'm riding the curve. Where are the y values heading as I ride along that curve, coming in towards 3 from the right-hand side? Well, it looks like I'm heading way up skyward. If you want to look at the equation, you say, well, what if I put in, say, 3.1? When I subtract 3, I'm going to get a very small number, but it's positive. So 12 divided by a very tiny positive, it's shooting off there to positive infinity. Hey, just a little note, if you want to kind of be redundant, just for clarity's sake, you could put a plus sign in front of that infinity sign. We don't usually if we're talking about positive infinity, okay? But if you want to clarify it, you can. Now that helps us understand that we absolutely have a vertical asymptote at x equals 3, okay? So my vertical asymptote is x equals 3. To get a feel for my horizontal asymptote, what I have to ask myself are these two questions. As I go off, or not me, as x goes off to infinity, what's happening to the function? Well, think about riding the curve. As you ride that curve and ride that curve and ride that curve, where's it heading? Looks like it's heading right to the x-axis. What happens if I put in a huge number, like a billion? 12 divided by a billion? It's very tiny. This guy is approaching 0. And I even know he's approaching 0 through positive values. Okay. Last thing, as I head off to negative infinity, as I'm going way out to the left, what's happening to the function? Well, it looks like I'm going to come up and rise and rise and rise and rise right towards that x-axis. Well, if I put in something like negative a billion, I've got 12 divided by negative a billion 3. It's going to be really close to 0, but it's going to be a negative number. So I know that I'm approaching that axis and I'm coming at it from below. It's so cool how you can think this through and have so much power. You know what this thing is doing. There's no question about it. And of course, when you get to calculus, you get to analyze these curves even more and get some even neater things you can analyze. Okay, so I have also a horizontal asymptote of y equals 0. Man, I know a lot about that curve. All right? And we're building a lot of knowledge that I think will help carry over, and then we won't have to be so ponderous as we look at some of our others. This should look a whole lot like 12 over x squared. What's the only difference between those two? Right here is showing a horizontal shift of 3. So we take that previous nice little curve that we had with all the symmetry on it and everything, and we slide it 3 to the right. And as we slid that whole curve 3 to the right, the asymptote, that vertical asymptote, slid over 3 as well. Hey, will I have a y-intercept on this one? Yeah, you can figure. If you know what this graph looked like, yes, I'm going to have a y-intercept. To get that y-intercept, put the 0 in for x, and we get what, 12 over 9? So 1 1/3. So around in here, I'm hitting it, and this is essentially the curve that I'm getting. Now, some of you might look at my graph and say, wow, that's just too quickly and too roughly made. Well, if you want better accuracy on the graph, what are you going to do? You're going to make lots of values. I just don't want to spend that time. And I figure if I need a gorgeous graph, I will take the time and make a careful table of values, or, much more likely to happen, I will go get some technology. And as I enter that equation into the technology to get a beautiful graph, I'm going to know that there was a vertical asymptote. I'm going to know that there is a horizontal asymptote going on there. I'm going to know it should be crossing the y-axis. And so I can look at whatever the technology gives me and say, yeah, that's good. That's good. Yeah? Are we okay with that? Now, I'm not talking about all of this. Maybe we ought to take a second. This notation means what? As x approaches 3 from the left, as you're riding the curve towards 3, and you're coming in from the left of 3, what's happening? You're going off to infinity, or the y values are going off to infinitely large values. This notation is saying as x approaches 3 from the right-hand side. So from the right-hand side, you hop on the curve and you're riding it, and boom, those values are headed upward. We're heading towards positive infinity. And again, if I put in extremely huge numbers, this guy is going to approach 0 from both sides. Hey, it looks like as I go out this way, I'm getting closer and closer to 0, but it looks like I'm staying positive, right? And over here, the same thing. Am I really staying above the x-axis both times? Or do I ever drop below it? Well, you don't have to think long and hard on that, because look, 12 is a positive value, right? When I square, that can't go negative, which means I cannot get any negative values out of this. My graph is contained totally above the x-axis. So its range, by the way, would be 0, open on 0, up to positive infinity. Okay? Well, now we got something totally different. Let's see what happens now. F of x is equal to negative 2x over x plus 4. Hey, what's the domain of this function? Because if you get into trouble and you're trying to figure things out, that's a fair thing to ask. Remember, domain is what can I put in? Well, I can take any number times negative 2, I can add 4 to any number, I can divide any real numbers. So the only problem is I can't divide by 0, so x cannot be negative 4. So I could say what's going to be all real numbers except, negative 4. Okay. So that means that, and I'm going to put a vertical line here right now. I'm not yet assuming that that is a vertical asymptote, but I know I cannot have a function. My function cannot cross that vertical line. Okay. Well, you know, because it's set up as a fraction, we kind of get an idea that lots of times we've got those horizontal and vertical asymptotes going on. So let's see if this is a vertical asymptote. And the way we check that out is by looking at this approaching idea. Since I don't have the graph, I'm going to have to look right here. As x approaches -4 from the left, now let's see here. Give me a number that's really close to -4, but to the left. Like -4.1 maybe? Okay, now think about this. If x is -4.1, I put that in the numerator, and what do I get? I get something like a positive 8.2 or something like that, right? So it'd be like about an 8.2 divided by, now what do I have in the denominator with a -4.1? I'd have a -0.1. Well, can you do 8.2 divided by -0.1 in your head? I know. You say decimals. Ah! It's not that bad. Move the decimal point. You get -82. Wow. So what that means is that puppy is dropping like a rock. Okay. So I know that, in fact, if I make this even closer to -4, that's just going to get to be a bigger and bigger number, only negative. So it's approaching -infinity. Now, what about as I'm approaching -4 from the right-hand side? Well, let's see here. So I'm going to put in a positive, well, not a 4.1, huh? How about if I put in -3.9? Because -3.9 would be really close, and he'd be on the right-hand side. Well, the numerator comes out to be like a 7.8. The denominator comes out to be, what, a positive 0.1? When you divide those, you get positive 78. So we're headed way up there. So guess what? We have a vertical asymptote. Our vertical asymptote is x equals -4. Hey, and you know what? That happened all because of this denominator, right? -4 is what makes it equal to 0. All right. Well, let's do a little bit more investigating here. For example, as x gets to be really large, as x approaches positive infinity, what's going to happen? Okay, so let's see here. What if we put in 100? Now, how close is 100 to infinity? Yeah, nowhere close. But if I put in 100, I would have -200 over, what, 104? What's that really close to? Maybe -2? Well, what if I put in 1,000,000? That would be -2 million over 1,000,004. Now, I think you can see that one's really close to -2. Agreed? Hey, by the way, is he a little bit bigger or a little bit smaller? Well, of course, we got the problem with the negative sign. If you think without the negative sign, that's actually going to be a little bit smaller, okay? But that's going to be like a -1 point something, so it would technically be above. You know what? This reminds me of the story that I was talking about Bill Gates and myself leaving a tip on a table. The idea that if you're talking about really large numbers, things like +4 just really don't matter. What really matters in this function when we start talking about large numbers only this negative 2x and the x. They're really the only ones that matter as x gets huge. So essentially what we do is we say, well, let's just consider that then. Negative 2x over x. We can cancel those x's, right? Because if we're heading towards infinity, we're a long way away from 0. And that's negative 2. Guess what? That means we have a horizontal asymptote at negative 2. Because as x gets huge, f of x is approaching negative 2. Now, by the way, it doesn't even matter what x is in this case. The idea being that we're ignoring the 4 because we're putting in really large values of x. But what I mean is, as we head off to negative infinity, the same thing happens. Wow. All right. Do you see, by the way, that these two, my vertical asymptote, my horizontal asymptote, have separated my coordinate axis system that Mr. Descartes gave us into 4 regions. You kind of see that there's 4 regions here. We know the domain is everything except negative 4. Now that means that I have to have my graph occurring in one of these two and in one of these two. All right? And I like you to be thinking about some of the really basic ideas as we go along. So let's find a nice easy point to get started. Let's find, if it exists, an x-intercept. A y-intercept where x is 0. If I let x be 0 and put that into my function, I get a 0 out. So you know what? I know this curve is going to go like this. Well, he doesn't touch that. I got a little bit far to the left. And then I'm going to be either in the upper part or in the lower part. Well, a very interesting way to analyze this, first off, you can grab a point. Like I could put in, say, negative 5 or negative 6 and see what kind of order pair I get. You're going to find something down here. Because you look at your factors in the denominator. This guy has a multiplicity of 1. Multiplicity? Remember we talked about that in a previous lesson? Whenever he has a multiplicity of 1 and we're talking about graphs of polynomial, he crosses the axis. Well, in this case, he crosses over your horizontal asymptote, and you're going to have part of your graph down here. Now again, if you're not comfortable with that, you could say, okay, what if I put in negative 6? What do I get out? Okay? And until you're really comfy, that might not be a terrible idea for you to do on your own till you feel really good with what's happening here. All right? Well, we keep building a lot of knowledge about things. I gave you an idea of what an asymptote is here. Sometimes students say an asymptote is a line that a curve never touches or never crosses. Well, we have to qualify that just a little bit. You've got to realize that an asymptote is not talking about the behavior that's in here close to your origin. All right? Asymptotes are talking about end behavior. It's talking about way out to the left, way out to the right, way up above, and way down below. So in that case, it's a line that your curve is going to get closer and closer and closer to, and as you're heading way out towards infinity, it won't cross it. But it might cross it in the nice little part in close to the origin. Okay? Now, these are some of our previous functions that we've looked at, and basically what I want to do is kind of put together some of the information that we've figured out along the way. For example, this guy had a vertical asymptote of x equals 3. You know, if you're keeping all this information and notes on the handout that you pulled down from Blackboard, it might be nice to lay these out next to each other so that you can see it. Okay, and so anyhow, you realize right here is y. Because when that goes to 0, we have that asymptote happening. Okay? Here we had an asymptote at 3. Here we had an asymptote at -4. Okay? These two both had horizontal asymptotes of y equals 0. Now, the reason is this. Remember, we're talking about really, really large numbers here. You take this 12, because he's the only thing I have in the numerator, and you take this x, because if I'm talking about large numbers, the rest of that doesn't matter. If I have 12 divided by x, what's going to happen is x gets insanely large. This guy's going to 0. So now you see how we find, or I say suspect, that we have these asymptotes. Well, we want to look at a few more here because, by the way, these rationals can just get crazy on us. So here's the graph for y equals 5x over x squared plus 7. Do you see a vertical asymptote there? Why not? Don't all rationals have vertical asymptotes? No. The vertical asymptote occurs, or you suspect that it may occur, where your denominator is equal to 0. Will this denominator ever equal 0? Not in the real numbers, and that's all I have here. So this guy has no vertical asymptotes. It's really cool. Now what about horizontal asymptote? Well, take the highest degree term out of the numerator. Take the highest degree term out of the denominator. Well, I could cancel an x out, and I would have 5 over x. As x gets insanely large, this approaches 0. So what you see, and it's extremely interesting, is that as we're heading out towards positive infinity, we're getting lower and lower and lower towards that x-axis. And on this side, we're coming up to it from below. And by the way, you could check symmetry and see that we have that beautiful symmetry with the origin. Hey, by the way, before we leave this guy, notice the curve crossed his asymptote. But I told you, that kind of stuff happens in close to the origin when your numbers are small, assuming that you have small values in here. It doesn't happen way out towards infinity. Okay? So, I said to suspect vertical asymptotes because in the next lesson we're going to have to put some fine points on this. But you suspect them wherever your denominator ends up equaling 0. And to get your horizontal asymptotes, you pull that highest degree term out of the top and bottom. Now the reason you're doing that is as we're talking about insanely large numbers, those are the only terms that will technically matter. Okay? So, let's real quickly graph this guy, because you see, that's our aim, is that we're going to get to be fast at knowing the big points. I look at this guy and I say, boom, vertical asymptote at -2. I say y equals highest degree term out of the top, highest degree term out of the bottom. That simplifies to 3. So this guy has a horizontal asymptote of y equals 3. Because this guy in the denominator, this factor, has a multiplicity of 1, I'm going to alternate and either go in these two positions or in these two positions. I know that for a fact. So if I simply find 1 point, boom, I got it all. Well, the easiest point to do is to put a 0 in. If I put a 0 in, I get 0 over 2. So guess what? I'm ready to call this. Now, this is not an accurate graph, but it's a very good idea of what my graph looks like. There we go. Using the ideas of the basics of rational functions. This guy has a vertical asymptote at 0. He's going to have a horizontal asymptote at 4. Well, darned it. The 0 is always the friendliest to put in, but I can't. So I'll put in one other value. Okay? Let's say 2. H of 2 would be what? 8 minus 6 over 2. We get a 2. Yeah? So guess what? And it'd be a good idea to find your x-intercept. We've got this going on, and then we're going to have this one. Hey, by the way, don't automatically assume that you always alternate. Remember, that happened because this has essentially a multiplicity of 1. Because if you look back to an earlier one, we had it hitting in both of the upper portions. Okay? What do you think? Vertical asymptote? None. Horizontal asymptote? By the way, why don't we have a vertical? Can you get that guy to equal 0? Mm-mm. What about y equals 4 over x squared? If x gets insanely large, we're going to 0. Okay. Now this one I think is really fun. Do you realize that the smallest this can be, the denominator, is 1? If I put in a 0, I get a 1 out of that, and 4 divided by 1 is 4. And any other time, it's going to get larger. The denominator is, which means 4 divided by larger numbers, they're going smaller and smaller and smaller. And I have y-axis symmetry. That's pretty sweet. So don't automatically assume that every time you see these rationals that you're going to have one here and one here. It doesn't always happen that way. Now, we'll go ahead and recap this and do some more work with it in our second session on rational functions. I'll see you in a few.